All right, so this video we're going to look at basic set concepts. It's going to be quite a long video, but let's see if we can get through it. So it's basically a lot of definitions, terminology. We'll do some examples and stuff. And the thing you've got to understand with sets is sets and working with sets is pretty easy as long as you know what the different words mean, the definitions are. And they're not difficult to remember. So let's go ahead and get started. It says a set is a collection of objects whose contents can be clearly determined or well defined. Okay, a set is well defined. Now, so what do we mean by well defined? Well, one example of a well defined set would be the collection of actors who have won Academy Awards. That's a well-defined set. You know, that only consists of actors that have won Academy Awards. So an example of a set that is not well-defined would be, let's say, the set of great actors. Okay? So the reason that's not well defined is because what you may think is a great actor, somebody else may not think is a great actor. So that's not well defined, and that's what they're talking about there. The objects in a set are called elements or members. Okay. Usually we refer to them as elements, the elements of a set, and you might hear somebody call them the members of a set. That's the different objects in a set. Capital letters are generally used to name sets. So whenever we name a set, it's typically with the capital letter. I mean, not always, but for the most part. Three methods commonly used to designate a set: word description, roster method, set builder notation. And I'm gonna show you examples on each of these. Okay, these are the three different methods we can use to designate a set. I mean, there could be others, but these are the most common. The one I like the best is roster method because it lists all the elements of the set, and you can see every element in a set. Sometimes there's so many elements in a set, it may not be good to write it in roster notation. In that case, a lot of times you'll see it in set builder notation. So right now, let's look at some examples and that deals with these three. So example 1, it says write a word description of the set. Okay, so we have set P consists of Washington, Adams, Jefferson, Madison, Monroe. Okay, so you can see this is the roster method. It lists each element of the set. Okay, so the way that we want to write this is as a word description. So we could write set P is the set of the first 5 presidents of the United States. And that is writing that set as a word description. That's what they mean. We describe the set in words. So if somebody gave you this, then you would know the exact elements of the set. You would know. So if somebody said set P is the set of the first 5 presidents of the United States, you would know set P consists of Washington, Adams, Jefferson, Madison, and Monroe. Okay. All right, so let's look at example 2. Set C is the set of U.S. coins with a value of less than $1. Express this set using the roster method. All right. So this time they gave us a word description of the set, and they want us to write it using the roster method. All right. So we would write C, and remember the roster method, that's listing each element. Okay. Now, before we go on, remember a set is surrounded by those curly braces. Okay. I know I probably don't draw them too good, but that's what we put a set in, curly braces. We don't use parentheses, we don't use brackets. You use braces, those curly braces, to represent a set. So this would be penny, nickel, dime, quarter, and we got $50. And that would be this set written in using the roster method, or written in roster notation or list notation, listing all the elements out. So we went from a word description to the roster method. All right. So let's look at the next one. Express this set using the roster method. All right. So this set that they give us is written in set builder notation. Now, here's how it's read. So set A is equal to the set of all X values such that, that's what that line is, such that X is a month that begins with the letter M. So the set A is the set of all X such that X is a month that begins with the letter M. So to write that using the roster method, well, what months start with the letter M? That's March and May. And so there is, using the roster method, writing the set down. All right. Let's look at the next example. So they want us to express this using the roster method. So L is the set of all X such that X is a lowercase letter of the English alphabet. All right, so all we have to do there is list out all the letters in the alphabet. So we have L is equal to, and that's a capital L. Let me write that a little better. So that would be A, B, C, D, E, and then I would have to write all the letters out. All right. So sometimes a set, if you're going to list it out using the roster method, sometimes you've got so many elements in a set that it's just not worth it to list every single element. I mean, you can see here that we would be listing out 26 elements, A through Z. So there is a way around that, okay? And you know, this set, it would have 26 elements. There's some sets out there that's going to have way more than that, okay? There's some sets that will have an infinite number of elements. All right, so to make things easier, we can shorten the way that we write these things, the way we list them out. So I've got the elements A, B, C, and then I can put 3 dots and then put the last element. And that's a Z. That's how I'll do my Z's, a Z with a line through it. That just helps you distinguish between a Z and a 2 a little easier. Okay? So this is a way that we could write this set out. We don't have to list every single element. So this means that this set contains the elements A, B, C, ... all the way to Z. And see, I've established a pattern here with the first 3 letters. And you can see that this would be A, B, C, and all I've done is I've left out D through Y. I didn't write all those letters out. But this right here makes it understood that D through Y is in there. So this would be A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, all the way to Z. Okay? So that's one way that we can write it out easier. Okay? We don't have to list every single element as long as you can establish that pattern that it's going to follow. All right. So that's the different ways that we can write sets out. Okay? Word description, roster method, and set builder notation. All right, so now let's look at the empty set. The empty set, also called the null set, I think most of the time you'll hear it called the empty set, is the set that contains no elements. The set is represented by these braces here with nothing in it, or this circle with a line through it. That represents the empty set. And here I have some examples of an empty set. So the first one, now both of these are written in set builder notation. So this is the set of all X such that X is a fawn, which is a baby deer, that speaks. Well, a deer can't talk. Okay, I know it makes sounds, but when it says speaks, it means talk words. So the set of all X such that X is a fawn that speaks, well, there's no fawn that does that. There's no elements for that set. So that would be the empty set. And then another one, we've got the set of all X such that X is a number greater than 10 and less than 4. Well, that's the empty set also. We know that can't happen. If you look at that, okay, here's 4 and here's 10. And the numbers that are greater than 10 are these numbers here, and the numbers less than 4 are here. Well, there's no number that's less than 4 and greater than 10 at the same time. There's not any numbers that do that. So that would be the empty set. Okay. Now, keep in mind, the empty set is not represented by this. Okay. This notation represents a set containing the element, the empty set element. Okay. So remember, the only way that you can represent an empty set is this or this. You cannot put this inside the braces. Okay. All right, so let's look at example 5. It says, which of the following is the empty set? All right, so let's look at part A. So is this the empty set? Okay, well, this would be what this one is no, because that's a set that contains the element 0. It's not empty. All right, what about part B? Okay, well, for one thing, 0 is a number. It's not even a set. Okay, so it can't be the empty set. So this would be no, not the empty set. What about the set of all X such that X is a number less than 4 or greater than 10? Okay, so that kind of sounds familiar, doesn't it? That might make you think of this set up here, but there's a difference. Notice in this set up here, it's separated by and this one is separated by or. So let's look at this one. So if I look at this, there's 4, there's 10, there's less than 4, there's less than 10. So I need a number that is less than 4 or greater than 10. So it only has to satisfy one of them in order to be an element of that set. So actually there's a bunch of them. Look at this. 5 would be an element of that set. It's less than 4. No, it's not greater than 10, but it doesn't have to be. It just has to be one or the other. Okay? I'm sorry. I don't know why I wrote 5. It should be 3. Okay? My bad. If you caught that before I caught it and changed it, then good job. You understand what's going on. All right, so 3 is less than 4. Okay? No, it's not greater than 10, but it only has to be one or the other. And look, 2 would be 1, 1, 0, -1, -2. Look at that. And then what would some other ones be? 11 would be in that set, 12, 13, 14 would be in that set. That set has an infinite number of elements, doesn't it? So this answer here would be no, that doesn't represent the empty set either. So what about this one? The set of all x such that x is a square with exactly 3 sides. So we all know what a square looks like. I know that may not be a very good one, but it's good enough. So we got a square. Well, we know a square has 4 sides. There's no square that has 3 sides. 3 sides is what? A triangle. So this one would be the empty set. Okay? Or you could put it as a symbol like that. Okay? I mean, I know they gave you 2 ways to do it, this or this. Typically, when they refer to the empty set, you'll see this one most often. Okay? All right, so hopefully we understand what the empty set is. See, like I said, it's a lot of terminology, and the problems that you'll have to work are actually pretty easy. They're not that bad. All right, so now let's look at notations. So the notations, this notation and this one, it's basically kind of like a, I mean, not really a C, but kind of like a C with a line in the middle. Okay, so this symbol is used to indicate that an object is an element of a set. Okay, that means, you know, this object, number, letter, whatever it is, this object belongs in this set. It's an element of the set or a member of the set. And then this symbol here, it's just this symbol with a line through it. You know, kind of like equals and not equal. Okay. So this symbol is used to indicate that an object is not an element of a set. All right. So let's look at some examples here. It says determine whether each statement is true or false. All right. So this one, R is an element of this set. Now we saw this set earlier, didn't we? Well, this is the set, the alphabet, right? A through Z. Remember the dots? That means that D, E, F, G, all the way to Y are included in here also. Now, is R included in here? Yes, R is a letter in the alphabet, so that would be a true statement. All right. So what about this one? It says 7 is not an element of the set 1, 2, 3, 4, 5. Okay. Well, is 7 in this set? No. So this would be a true statement because it says 7 is not an element. Now, what about this one? It says the set A is an element of the set AB. Well, this is a set. So it's not an element of this set. So a set cannot be an element of another set. Okay? This is the set A. Okay? Well, let me take that back. The set A is not in here. The only thing that's in here is A and B. See, it would have to look like this in order for it to be an element. All right? But see, all we have is the AB. All right? So hopefully that makes sense of element and not an element. All right, so before we go on to these other examples, let's look at the set of natural numbers. So the set of natural numbers consists of the numbers 1, 2, 3, 4, 5. Okay, what do these dots mean? Well, the set of natural numbers are all the numbers from 1 to infinity. Okay? And there's no way we can write that out. So what we do is we just write a few a few elements, 1, 2, 3, 4, 5, establish the pattern, and then the 3 dots. And when nothing comes after the 3 dots, that means it just goes on forever. Okay. All right, so let's look at this. Express each of the following sets using the roster method. Set A is the set of natural numbers less than 5. All right, so I've got A is equal to, so we know what the natural numbers are. We looked at that there. That's 1 to infinity. So set A is the set of natural numbers less than 5. Okay, so that would be 1, 2, 3, 4. Now, is the 5 going to be included? Think about that for a second. The set of natural numbers less than 5. So 5's not included because they want the ones less than 5. So that's just 1, 2, 3, 4. All right. What about set B? Set B is the set of natural numbers greater than or equal to 25. All right, so B, okay, so B would be what? 25, 26, 27, 28, greater than 25 or equal to 25. So that would be 25, 26, 27, all the way to infinity. Okay, so that's the set of natural numbers greater than or equal to 25. All right, so what about E? E is the set of all x such that x is an element of the natural numbers and x is even. So on this one, it actually has to meet both criteria. Okay, it has to be a natural number and it has to be even. So for this one, E, now before we write the set out, can you tell me, well, not tell me, but think about it. What form is this set written in? That's right, set builder notation. All right. All right, so set E is the set of all x such that x is an element of the natural numbers or x is even. So let's see, the natural numbers are 1, 2, 3, 4, 5, 6, 7, and so on. So we just want the even ones. So that would be 2, 4, 6, 8, and so on. All right. So let's take a look at the next one. The set of all x such that x is an element of the natural numbers and x is less than or equal to 100. All right. So that would be the set. So it has to be a natural number and less than or equal to 100. So that would be what? 1, 2, 3, 4, and so on. Whoop, I'm sorry. And so on. Now, let's just erase this. Do we just leave the 3 dots and put the brace there? No, because if we did, that would be 1, 2, 3, 4 all the way to infinity. But what does it say? It says it has to be less than or equal to 100. So that means we're stopping at 100. So this represents all the numbers from 1 to 100. All right, what about this one? The set of all x such that x is an element of the natural numbers and, now what does this mean here? That just means x is between 70 and 100. Okay, so I'm going from 70 to 100, right? I need all the numbers in between these two. Now, before we go on, let me ask you this. Is 70 going to be an element of the set? Yes, 70 will be an element because it says less than or equal to. That line underneath means the 70 is included or equal to. Now, is the 100 going to be included? No, the 100's not going to be included because it's just less than. It's not or equal to. All right, so this set is going to be the numbers from 70 all the way to, and here it says to 100, but not including 100. Okay, so that would stop at what? 99. And so there's that set. Okay. All right, so I hope you're getting all this. All right, so let's look at the next one. The cardinal number of a set A represented by, and this is read N of A, is the number of distinct elements in set A. And, well, just what I said, this symbol is read the number of A. Or, I'm sorry, not number, but N of A. Okay? So the cardinal, it's how many distinct elements are in the set. Okay? So let's look at these examples here. So we have set A is equal to 7, 9, 11, and 13. All right. So to answer this, we've got N of A is equal to what? 1, 2, 3, 4. And there's your answer. Okay. You see how easy that is? All right. So what about this one? What's the cardinal number of this set? Well, that would be N of B. That contains the element 0. So the cardinal number for that would be what? 1. There's one element in that set. All right, so what about set C? I need the number or the N of C. Well, remember this 13, 14, 15 all the way to 23, okay? So that also means that in this set that the number 16, 17, 18, 19, 20, and 21 are also included in this set. See, this is 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, so if we count all these numbers up, well, that would be what? 11. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 elements. So that would be N of C. Now, what about this one? N of D. Well, this is the empty set. And remember what we talked about earlier, the empty set has how many elements? None. So that would be 0. All right. All right, so let's look at the next one. It says a set A is equivalent to set B means that set A and set B contain the same number of elements. So if we have equivalent sets, that means N of A and N of B are the same. They equal to each other. Okay? That's this up here. Okay? The cardinal numbers are the same. Okay? That means they're equivalent. Now, remember, it doesn't say they're equal. It says they're equivalent. All right, so now let's look at this. One-to-one correspondences and equivalent sets. All right, so a one-to-one correspondences and equivalent sets, if set A and set B can be placed in a one-to-one correspondence, then A is equivalent to B, meaning N of A is equal to N of B. And if set A and set B cannot be placed in a one-to-one correspondence, then it is not equivalent to B. And that just means N of A does not equal N of B. All right, so let's look at an example here. All right, so we've got this this chart here, and what they want to know, it says it shows the top 5 impediments to academic performances of U.S. college students. That's what this shows. So what they want to know, are these sets equivalent? All right. So let's look at this. Now, I want you to keep in mind that these this right here, these are percentages here. So that's like 5%, 10%, 15%. So they're percentages. All right, so let's write out these sets. Okay. So let's just call set A. Let's see, where can I write that? I'll see if I can fit it in right here. Set A, that's the impediments here. So that would be stress, sleep, illness, anxiety, and work. Okay, I just abbreviated anxiety because I wouldn't have had enough room to write it. All right, and then let's have set B represent the percentage of students reporting each impediment. So we've got reported here, we've got a 28, a 20, a 19, and another 19, so you don't write it twice, just write it one time, and a 14. All right. So we can see here that stress, that corresponds to 28. Okay. Sleep corresponds to 20. Illness corresponds to 19, and so does anxiety. And then work corresponds to 14. All right. So you can see that illness and anxiety correspond to the same number. Okay? So there's no one-to-one correspondence here. Okay? And so we could say here that these sets are what? Not equivalent. Okay? You see, we can say A and B are not equivalent. Because remember, in order for them to be equivalent, and well, this is another way we could look at it too. The number in A does not equal the number in B. Okay? So they're not equivalent. Okay? Because see, n of A is what? Is equal to 5. 1, 2, 3, 4, 5. And n of B is equal to 1, 2, 3, 4. And from earlier when we went over that equivalent sets, these n of A and n of B had to be equal. They're not, so those sets are not equivalent. Okay. All right, so let's look at this one. Set A is a finite set, is n of A. So in order for A to be a finite set, n of A has to equal 0, or n of A is a natural number. A set whose cardinality is not 0 or a natural number is called an infinite set. All right. So when you look for the cardinality, remember n of A, when we found that, n of A, the number of distinct elements in a set, okay, when we found that, if that equals 0 or one of the natural numbers, then it's a finite set. If it doesn't equal either one of those, then it's infinite. Okay, that makes sense. So here's an example of an infinite set. The natural numbers. 1, 2, 3, 4, 5, and then it just keeps going on forever. Okay, that would be the set of natural numbers is an infinite set. All right, set A is equal to set B, means that A set A and set B contain exactly the same elements, regardless of order or possible repetition of elements. And the way that we write this in symbols is A equals B. Okay, so that makes sense. In order for two sets to be equal, they have to have the same exact elements. Okay, so here's an example of that. If we have set A is equal to WXYZ and set B is equal to ZY, W, and X, well, are those two sets equal? Well, let's see. So let's see, we've got W, and over here we got W. We've got X, and over here we've got X. Here we have Y. Here I have Y, and here I have Z, and there I have Z. And that's it. All the elements match. Are they in the same order? No, they're not. But remember, what did it say? Regardless of order. Okay, so we can say set A and set B are the same. Okay. All right, so let's look at this. Determine whether each statement is true or false. All right, so I've got the set 489 is equal to 894. Well, what is this? That would be true. They have the same elements. Okay, they got the same elements. Well, what about this one? 135, is that equal to the set 0135? No. See, this one has the element 0 and this set doesn't. So this would be false. All right, and another thing that I want to mention, I want to point out here, is that if, let's write this, let's write this. If two sets are equal, then they must be equivalent. Okay, so if you have two sets that are equal, then they're also equivalent. Now, let's go back the other way. If two sets are equivalent, does that make them equal? Well, let's see. So what if I have the set, say 1, 2, 3, and then I have another set, A, B, C. Okay, so let's just refresh our memories, our memory up here. A set A is equivalent to set B means that set A and set B contain the same number of elements. So the number of A is equal to the number of B, or N of A is equal to N of B. All right, so, well, let's see. Let's just call this set A. Let's call this set B. So let's see. N of A is equal to 3. N of B is equal to 3. Oh, look. Those are the same, so they are equivalent, but are they equal? No, they're not equal because they don't have the same exact elements. Okay? So that's something there that you know, that would be good to remember that. If they're equal, then they're equivalent. If they're equivalent, that doesn't necessarily mean they're equal. Okay? It doesn't mean they're equal. All right? And what I just did then is when I asked you that question, if they're equivalent, does that make them equal? Do you see what I did? I went back up to the definition. Okay? I went back and looked and read what it said equivalent sets are. And that's all I did. I just read that and I applied it. That's all this is. If you can just go back and look at these definitions and read them, it tells you exactly what it is. And hopefully going through this and going through the definitions and then working some examples like that, hopefully that got you to understand the what the definitions mean and how to read them. All right, so that's all of this video. The next video will be on subsets. Okay, this is going to be contemporary math lecture series, I guess we can call it, but that's what it is. And I got a contemporary math book, and I'm just going through each section and just doing a lesson on them, on each section individually. So I hope you like it. Hope it helped. Give me a like, share, and subscribe. Check out my other videos, and thanks for watching, and I'll see you later.